Hello everyone. In this video we'll be looking at section 7.5, which is work. Work is another application of the definite integral. So in general, work is done by a force when it moves an object, right? Think physics here. So work done by a constant force formula. If an object is moved a distance d in the direction of an applied constant force, the fact that it's constant is very important here. That's the only time we're allowed to use this formula for work. Then the work done by the force is defined by work is equal to, here I'm going to write it out explicitly, force times the distance. That's if it's constant, right? So in other words, we call force F and we were calling the distance big capital D. Okay. So that's our formula for work. There are four types of forces. There's gravitational, electromagnetic, and then strong nuclear. And if there's strong nuclear, then there's probably weak nuclear. Right? So we're not going to go into too much detail on that, but I just wanted to have you know that for a little bit of background. So in general, force can be thought of as push or pull. The basic unit for force in the International System of Units, or SI units, is the Newton, right? And that's the force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram. That's not a typo. It's 1 meter per second on a mass of 1 kilogram. So that's explicitly what it means to be a Newton, but in general, that's just our unit here. And that's our SI unit. The basic unit of work in SI, so I'm sorry, that was force, is newtons, and now work, basic unit, is called Newton meters or joules. Right? Okay, so we have this nice table here that lists the SI units for work, which is joule, we just found out, the unit for force, which is Newton, and the unit for distance, which is meter. The US we know is a little bit funkier, but the unit for work there is called a foot-pound. The unit for force is pound, right, because weight is a force, and then the unit for distance is foot. And then we have a couple of conversion formulas there to help us out. So now our first question here, determine the work in lifting a 50-pound object 4 feet. So in this case, the work is constant. So because the work done in lifting a 50-pound object 4 feet is constant, we can just use our work formula, right? Work is equal to the force times the distance, right? So the force is the weight of the object, right? So remember, force is the weight, right? So when I put force here, I should get 50 pounds because that's the weight. And then how far am I lifting it? I'm lifting it 4 feet, right? And notice when I multiply these two together, I get 200. And what's my units? Foot times pounds. In other words, foot-pound, right? That's why we have that is foot-pounds is our unit of work. Okay, so that's a very simple case. Oftentimes, though, work is not going to be constant, right? Sorry, this is kind of acting up on me. Oftentimes, work is not going to be constant. Please don't do this right now. Try to exit out of the app here. Let's see what we can do. All right, oftentimes force is going to be not constant, right? So when a variable force is applied to an object, I'll highlight variable here, calculus is needed to determine the work done because the amount of force changes as the object changes position, right? So for example, the force required to compress a spring increases as the spring is compressed, right? As it gets more compressed, it gets a little bit harder to push the string together. Okay, so consider an object that is moved along a straight line from x equals a to x equals to b by a continuously varying force function f of x, big F of x. Let delta, that's just a fancy name for what we call the partition. Remember, partition just means break it up into little pieces, right? So let delta be the partition that divides our interval from A to B into n different subintervals determined by A equals x sub 0 all the way up to B, right? This should remind us of what we've been doing with our definite integrals so far in the course. Right, so let's go ahead and draw a picture of what we've got going on here. So let's draw my force function here. Maybe a little bit neater. My force function here, so this is my big F of x, and I'm moving this object from A to B, right, on my x-axis here. Here's x, here's y, right? And so now what we're going to do is, just like before, we're going to partition this. This time we're going to do it for, let's say, n equals to 3. So we're going to make this 3 different partitions here. So this would be our x sub 1, this would be our x sub 2, B is going to be our x sub 3, and A is going to be our x sub 0. And just as before in the other videos, we're going to call this delta x sub 1, delta x sub 2, because remember delta stands for change, and this as delta x sub 3. Okay, so now we move on here. For each I, you're going to choose some x value c sub I such that x sub I is that c sub I is between x sub I and x sub I minus 1. So in other words here, I'm going to call this c sub 1. It's going to just be some point in between our two x values. We'll call this c sub 2, and we'll call this c sub 3. So associated with that c sub 1, since that's an x value, it has this y value, right? This is f of c sub 1. C sub 2 has this y value, f c sub 2, right, because our function is called f. And c sub 3 has this y value that is f c sub 3. Okay? So what we're going to do here is we can approximate the total work done on just one of those intervals, right? So say from A to x sub 1, by assuming that the work on that little interval is constant and equal to f sub ci. So in this case, if I were going to look here, I'm going to assume that on this interval from A to x sub 1, right, so on this interval here, that the whole time, instead of being equal to the purple part, that it's equal to the red part, right, or the height of f sub c sub 1. And same thing here, and same thing here. Right, so on each of those intervals, instead of the force being given but changing for each x value on the interval, I'm just going to assume that it's equal to that height, either f of c sub 1, f sub c sub 2, or f of c sub 3. Right, so I'm going to assume that the force is constant on that little interval. Well, if the force is constant, we know the formula for what the work should be on that interval. So we're going to call the work on that interval W of I. All right, so let's write it in pink here. We'll call the work W sub I. And what is the work W sub I? Well, remember, work is just force times the distance. Right, so the work on this interval right here from A to x sub 1 is going to be the force times the distance. Well, force, remember, is the height of this bar here. The distance is just going to be the distance that it travels, the distance from A to x sub 1. Well, A to x sub 1, that distance is delta x sub I. So the work that we're finding, this delta W sub 1, is just going to be the area of that rectangle right there. And if I find the work on the second interval, here, the area of that piece is delta W sub 2, and then the work on this third piece is delta W sub 3. Right? So again, on each one of these intervals, I'm assuming that it's constant, right? And I'm assuming that it's equal to this random f of c sub I value. And since it's constant, we can use that formula. But then, if I want, that was just the work on each interval, right? Delta W sub 1 was the work on the first interval, delta W sub 2 was the work on the second interval. So if I wanted to know the total work, then I need to add all those up, right? So the total work can be approximated by taking, in general, we did this for 3 in our picture, but in general, I would have I of those little rectangles, I of those little pieces of work. I'd add them all up, and I would get my total work, right? But what is delta W sub I? How did we get that work? Well, we took the force for some intermediate value and said it was constant, and then multiplied it times delta X. Now, anytime we have these summations, you should be getting used to this by now. I can take infinitely many of those partitions, right? In other words, infinitely many of those rectangles. And if I take infinitely many, in other words, if I take the limit as n goes to infinity, we know that our summation goes to an integral, and we know that our delta x goes to dx. And so we have an integral, right? So this leads us to our formula for the work done by a variable force. And our formula is, I'm going to write 2 different formulas. I'm actually going to write the second one first. The second one is going to be the one you were expecting. That work is the integral from a to b. And now, if we look here, the summation goes to being a, whoops. I need to put a summation sign before this. Because I'm adding up all of these works. So the summation sign goes to be the integral, so that's where I get the integral from a to b. And now my force function is just f of x for force, and then my delta x becomes the dx. So that was the one you're expecting. I'm also going to write that limit definition as well. So work is equal to the limit, and I'm going to put this kind of strange looking thing here, but it makes sense. So remember, what is delta? Delta is that partition. So what this is saying is if I have, if I make my partition have infinitely many pieces in it. In other words, if I make that n go to infinity, right? So if I do that, then I have my formula here, which is the sum I equals 1 of delta W sub I. Right? In other words, my adding up my works. Okay, so I'll go ahead and end that here, and we will talk about Hooke's law in the next video.